A very good morning to everyone to the Organic Chemistry Marathon. How are you all doing? Very good evening, a very good morning. Just tell me your names quickly and which class are you studying in. Most of you would be in class 12th and preparing and giving your NEET this year. And if someone is a dropper, just mentioned as a long term. I can't see the screen. Okay, just mention your name, mention your class, and then we are going to start our session. Then we'll start our session. If you people feel fear of organic chemistry, then I would try to decrease your fear or completely finish that fear in today's class. Okay, it's a little long class being a marathon. Okay, we'll be taking 3 to 3.5 hours of class, and I'll try to brush up all the concepts. Hi Chandana, hi Gayatri. We'll try to finish up the concepts within 3 hours. This class is mostly going to be a concept class, and there will be one more. Hi Saimanu, yes, good. So, hi Suresh, good morning. Chandana, good morning. Gayatri, good morning. Now I can see your chat as well. Incoming senior. Okay, Gayatri. So, this is going to be a concept class. Today is a concept class. Concept marathon. After few days, after 1 week, most probably on 23rd or 24th April, by the time you clear your concept, I will be taking one question class as well. Question/problem practice, where I will be telling you 100 most important MCQs from the organic chemistry. Okay, so this is going to be, hi Tejaswini, hi, good morning, Soumya, Lakshmi Narayan Reddy, hello, Gamya Hasini, very good morning. I'm from long term Idbugulu, that's very good, Lakshmi. All right, guys. Then let us start our class. So you can keep this in mind. You'll get the update about the next class as well, which is going to be a question or problem solving class. 100 most important MCQs of organic chemistry L10. Very helpful for NEET, Gamya. I have prepared the lecture in such a way that even if you are at a lower level of preparation, you will be benefited with it. Even if you are at a higher level of preparation, then you will feel more confident after this class. Okay, so keep your books ready, keep your pens ready, keep your water bottle ready, and keep sipping of the water also in between. Okay, let us start, everybody. So I'll go very quick in the easier concepts, and I'll go slow in the more difficult concepts. Okay, thank you, Soumya. Now I'll be focusing only on the camera, not on the chat box. You can keep the chat box off for at least 1 hour. Don't keep it off, but you don't chat. Okay, 1 hour. After 1 hour, I'll start the chat again. Okay, so all of us know about hybridization. So carbon has a good catenation property. Carbon makes 4 bonds at a time. All of us know. Catenation property is due to very stable multiple bond formation of carbon. So carbon can make multiple bond, which is pi bond, 2p pi, 2p pi bonds, which are very stable due to its small size. Okay. And high bond energy of carbon makes single carbon bonds very stable. So carbon shows good catenation, tetravalency at a time. Hybridization of a carbon, how to decide? Just count the number of sigma bonds. If number of sigma bonds are 2, number of sigma bonds are 3, number of sigma bonds are 4, 2 sigma bonds sp hybridization, 3 sigma bonds sp2 hybridization, 4 sigma bonds sp3 hybridization. Okay, so if any structure is written, we can easily tell the hybridization. Like this is ethane, all of you know, ethane has all sp3 carbons because carbon is having 4 sigma bonds. Ethene is going to be sp2, 1 sigma, 2 sigma, 3 sigma. 3 sigma means sp2. Alkyne, 2 sigma means sp. Okay. So you can tell me how many sigma and pi bonds are present in the following molecules. I'll just quickly do this one, and then I'll ask you questions after some time. So let me do this one. You can see here. So whenever you want to find sigma and pi bonds, just open the molecule completely and check. 4 carbons are there. This carbon is attached to 3 hydrogens. This carbon is attached to no hydrogen. This carbon has no hydrogen. This carbon has 3 hydrogens. Okay. So easily we can find the number of sigma bonds. These are the sigma bonds, the skeleton that I have made. And this is a pi bond, this is a pi bond. So there are 2 pi bonds and 1, 2, 3, 4, 5, 6, 7, 8, 9 sigma bonds. This is the simplest type of problem you can get, and it is possible to get these problems in NEET as well. Okay, from the chemical bonding part you can get such type of problems. Other ones also you will be able to check yourself. Right now don't write anything. Wherever I mention those questions you can write. Right now we are just doing basics, so I'll tell you the more important parts in slow manner and these basic parts in very fast manner, so that we get rid of all these things which are there in the syllabus. Just you get a gist of it, what all things are there. There are 4 ways to write a structure: Lewis dot structure, dash structure or bond line structure, condensed structure. Dash structure means a complete structure. So if I write for, let's say, propane, Lewis dot structure you don't have to write right now, it's from the chemical bonding part. Dash structure means completely writing propane by opening 3 carbon, CH3, CH2, CH3. All of you know this. Condensed structure means just writing CH3, CH2, CH3, means do not show any bonds but show all the atoms. Do not show any bonds but show all the atoms. And bond line structure means just showing carbon as dots and then their bonds. Hydrogens are invisible here. This is propane, right? These are the structures you can see here. Condensed formula: propane becomes this. This is propane 1-ol, propane 1-ol, 3 carbons and an oxygen. 1, 2, 3. 3 carbons, 3 dots and 1 OH. This is the one. Like that we can mention. If multiple bonds are there, accordingly you will draw. For example, just one example I'll show you. If something like this is written, so I can convert this bond line structure into condensed formula also. So it is nothing but wherever you see there is a sharp turn coming, that's a carbon. So there is a carbon, there is a carbon, there is a carbon, there is a carbon. And these are also all carbons. Okay, then always try to complete the valency of carbon in a bond line structure with the hydrogens. So whatever valency you are able to see, that many, and 1 extra, 2 extra hydrogens you can keep. For example, this carbon already has 4 bonds, tetravalent. 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 This carbon has 3 bonds, so 1 hydrogen, 1 hydrogen, 1 hydrogen, 1 hydrogen, 1 hydrogen. Correct? So this is the one. You can tell the molecular formula also now. So it is a carbon how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C10. Hydrogens how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 hydrogen. Oxygen how many? 1, 2, 3. 3 oxygen and 1 nitrogen. So this is going to be the formula. Yes. Okay. Moving on. Classification of organic compounds. So organic compounds are of basically 2 types: open chain, closed chain. Open chain is called as acyclic. You can ignore Gayatri, anybody messaging you, and you can ignore that. Just focus on the class right now. Okay, all of you. So cyclic, acyclic. These are acyclic ones. These are cyclic ones. Okay. When we talk about acyclic ones are further straight chain, branch chain. Propane is a straight chain, butane is a straight chain, isobutane is a branch chain. All their namings and all will keep coming. Unsaturated is saturated, means alkanes and alkenes. Alkanes are saturated. These are alkanes. Alkenes are unsaturated. Alkynes are unsaturated. Okay, benzene is unsaturated. and so on. You should remember what is cumulated double bonds, conjugated double bonds and isolated double bonds. Okay, you should know this meaning when they ask you which is a cumulative double bond, which is a conjugated double bond, and what is a isolated double bond. Remember this forever now. Beta, cumulative means two pi bonds occurring together. Two pi bonds occurring together. For example, one carbon carrying two pi bonds on each side. CH3, C double bond, C double bond, C CH3. This is called as a cumulation together, two pi bonds together at adjacent position. Conjugated means at alternate position. So here two pi bonds alternate, here two pi bonds adjacent next to each other, and here two pi bonds anywhere. They should not be cumulative, they should not be conjugated. So conjugated, for example, something like this, pi, nothing, pi. This is conjugated. Pi bond, then no pi bond, then pi bond, then no pi bond, like that. Isolated means they are not occurring at alternate position, they are not at cumulative position also. So this is an isolated example. I hope everybody is clear with this. Okay. Cyclic or closed chain can be homocyclic or heterocyclic. Homo means only carbons in the chain, in the ring. Hetero means any other atom in the ring. Most common example of heteroatomic is pyridine. This is pyridine. If I do not draw this circle in the middle, means if I make it non-aromatic, it is going to be called as pipyridine. Piperidine, pipyridine, like that. Okay, so aromatic, aliphatic, two types are there. Aliphatic also we can call it alicyclic. So heterocyclic are of two types, ali and arrow. Ali means those who will not follow the Hund's rule. Arrow means those who will follow the Hund's rule. What is Hund's rule will be coming later. Same way homocyclic also two type. Alicyclic, like if I make cyclopropane, if I make cyclobutane, cyclohexane, these are all alicyclic. Aromatic, if cycloalkene, cycloalkadienes, these are all alicyclic. They do not follow the Hund's rule. If they start following the Hund's rule, they become aromatic, like benzene, like naphthalene, and so on. Phenol, and so on. Okay. These are few examples. You can just quickly have a glance at them. If you can see their names, all of you must be knowing their names by now. Cyclopentene, cyclohexene, aromatic, benzene, toluene, you should remember them. If there is one more CH3, it becomes xylene. This is toluene, this is xylene now. Toluene, xylene, all these you should know. Naphthalene, when two benzene rings are fused together. Anthracene, three are fused together. Heterocyclic, this is pyrrolidine. These are all alicyclic ones. Okay. You can just take a screenshot, remember their names. Any name in the NCRT must be learnt. Okay. Any name which is there in the NCRT must be learnt. Pyrrolidine, tetrahydrofuran, pyran. They are not following the Huckel's rule. They are not aromatic. So they are aliphatic. These are the aromatics one. Three of them you should learn at least: pyridine, furan, pyrrole. All of them have 6 electrons in conjugation. 1, 2, 3, 4, 5, 6. 6 electrons in conjugation. 1, 2, 3, 4, 5, 6, this lone pair. So 6 electrons in conjugation, Huckel rule is valid. 1, 2, 3, 4, 5, 6, aromatic. Aromatic compounds are very stable compounds, all of you know. Now the question is for you, quickly answer it everybody. Quickly answer it. I'll keep those notes. No problem, Lakshmi. Lakshmi Narayan, I'll keep that. Quickly answer it. A, B, C, D. Quickly. 2 seconds. Within 2 seconds, give me the answer. B, C. Alicyclic compounds are aromatic, cannot be aromatic. Aliphatic cyclic compounds, this is the perfect answer. Heterocyclic compounds, no, alicyclic means just which are not, cyclic means cyclic, ali means not aromatic. Anything which is not aromatic is alicyclic. Anything which is not aromatic, cycle. Shravani, very good morning, beta. Okay. So, alicyclic means anything which is cyclic. It may be hetero, like piperidine. It may be homocyclic, like cyclohexene. Both of them are aliphatic. Aliphatic cyclic compound. Okay. Yes. B is correct. Heterocyclic compound may be aromatic, may not be alicyclic, like pyrrole. So, if I took pyrrole, pyrrole does not satisfy alicyclic condition. Next one. Which of the following is a heterocyclic compound? Quickly, hetero. Which is a heterocyclic compound? Heterocyclic compound. Quickly answer. You would have seen these structures somewhere. B. B is very good. B is correct. Thiophene is just like furan but with a sulfur in between. This is thiophene. Yes. Phenol has oxygen, but oxygen is not inside the ring, that is outside the ring. So it is again a homocyclic only. Aniline has a nitrogen, but that nitrogen is outside the ring. If inside the ring there is a heteroatom, then we'll call it hetero. Pyrene is CCl4. Okay, tetrachloromethane is called as pyrene. Okay, this is the one. Next one. Some common names, let us see, then we'll see few IUPAC names. Methyl alcohol is called as wood spirit. Methyl alcohol is also a common name for this. Urea, marsh gas, vinegar, acetic acid. Oxalic acid, which is 2 carbons together, ethane dioic acid. Then there is formic acid. Then there is lactic acid, a optically active acid, which is lactic acid. It contains a chiral carbon here, CH3, CHOH, COOH, lactic acid. Okay. Then there is malic acid. Okay, malic acid. Not much important to learn the malic acid. You can forget about it. Then there is butyric acid, 4 carbon. You can leave these one as well. Now, when we come to the, good morning Indra, when we come to the IUPAC nomenclature, means systematic nomenclature, we have a name with 3 parts. Every name can have 3 parts, not always, but can have, which is word root, which will tell you number of carbon, meth, eth, but, prop and all those. Suffix, which will tell you about the bonding in the hydrocarbon, whether it is alkane, alkene, alkyne, and which functional group is present. And then we have prefix, which will tell you the other things. So, for example, when I take a name, how many carbons are there in the parent chain? Word root will tell us. Okay, all of you know that. What type of parent chain is there? Is it saturated or unsaturated? Primary suffix will tell us. So, primary suffix tells you about ane, ene, ine, alkane, alkene or alkyne. And there is secondary suffix which attaches to the last, which tells you about main functional group. Main functional group. Prefixes are not always present, but secondary prefix most probably will be present. Secondary prefix tells you about substituents which are present. Substituents, okay, alkyl chains, other functional groups. And primary suffix is generally rare. It will tell you about if a carbon ring is cyclic or not. If your parent chain is cyclic, then this will be present, like cyclohexane. Okay, cyclohexane. So one example, let me give you. All of you can see here. If I say something like 2-methyl cyclohex 3-ene 1-one. Okay, let's say this name I have mentioned here. 3-ene 1-one. If I mention this name, then whenever you look at a name, hi Hari, hi Manasa, whenever you look at a name, always find the word root first. word root, which will be either meth, ith, but or so. I can see a hex here. So this hex is word root. Means there are 6 carbons in the parent chain. Then after you have found the word root is a must. It has to be present. Primary suffix is a must. It has to be present. So whatever attaches after word root, 3 in, this is primary suffix, 3 in. This may be present, may not be present, not must. It is an optional thing. If anything is present after in, it is one on. So this is secondary suffix. Means ketone is present. This is also not a must, secondary also not a must. Anything before word root, if you see cyclo written, cyclo is going to be your primary prefix. This is your primary prefix. And rest everything becomes secondary prefix. So this structure is nothing but cyclo means cycle, hex means 6 carbon, cyclohex. This is cyclohex. This is cyclohex. Okay. Then you number according yourself. Anywhere you keep number 1. You think that this is number 1, let's say. This is number 2. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. At number 3, there is a alkene. So at number 3, there is a alkene like this. At number 1, there is a ketone like this. At number 2, there is a methyl like this. So this is the compound. Okay, how we have reached to this name, all of you know the rules. Those rules I will be teaching you now. So this is about the 3 parts of the name. Okay, all of these things I have told you. All of you know the word root already. Okay, many times you have studied this. We'll directly go for the rules now. Now rule is simple. You should remember that there are 3 rules. Mostly 2 rules will work. Third rule is very rare. Rule number 1, parent chain selection. Parent chain selection. Rule number 2 is lowest locant rule or numbering of parent chain. And rule number 3, if rule 2 fails. Rule number 3, use if rule 2 fails. In case rule 2 fails, then go for rule 3. The name is prefix rule. 3 basic simple rules are there to name any particular organic compound. Now, every rule that you have to follow, you have to give maximum preference to secondary suffix. This is most important person for us. Then primary suffix. Then word root. Then prefix. What do we mean by this? What do I mean by this? Means when you are taking parent chain, your main functional group carbon must be included. That is your first preference. After you have included main functional, who is a main functional group? The functional group which is higher in the priority. Priority order is there in the NCERT, you can check. Carboxylic acid comes first, then sulfonic acid comes, then carboxylic acid derivatives come. All of you know the priority. After you have taken the main functional group, your main motive is to take unsaturation. Means alkenes and alkynes. Word root means number of carbon. So you try to maximize the number of carbon. So our aim is not just to maximize the number of carbon. So the name of the rule is not longest parent chain rule. There is nothing like that. We need a parent chain which contain main functional group, not the longest chain. After you have done that, you have to take maximum unsaturation, then maximum number of carbon, and then maximum number of substituents or branches. So first you will try to take main functional group. After you have taken that, you will try to take more and more unsaturation. After you have done that, you will try to take more and more carbons. After you have done that, you will try to take more branches. Okay. Let me show you a few examples now. Just the selection of parent chain I am showing you right now. Okay, just the selection of parent chain. All of you can see here. If I have something like this, let's say, or let me keep it little simple for you. If I have something like this, let's say, Now when I want to select the parent chain, my aim is not to maximize the number of carbons. My aim is only to start from here. I want my secondary suffix first. So I'll look for a functional group. Okay, I find a aldehyde. He has a surname Al. This person says I must be taken in the parent chain. Okay, we will take you. Then I will think, where is the alkene? These two carbons are the alkene carbon. They say we must be there in the parent chain. So I don't have any option. I have to take this as the parent chain. This is the parent chain. Second rule is numbering rule. Same rule applies again. Numbering rule. Lowest number should be given to main functional group. So I have to start numbering from here. 1, 2, 3, 4. So it's a but. It's a 3-ene. It's a 1-al because aldehyde surname is al. But 3-in-1-al. At number 2, there is no cyclo, so there is no primary prefix. At number 2, we have this group attached, which is 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon. This is called as pent because 5 carbon, yl because it's a side chain, pentyl. So it's a 2-pentyl but 3-in-1-al. So the rule is not longest chain rule, it is parent chain selection rule. Is this clear to everyone? Can I move ahead? Yes or no? Can I move ahead, everybody? Yes. Okay. All right. Let's see one more example, everyone. Let's see one more example. Let's take this example now. Yes, good morning, Chinu. First, I would want to take my parent chain. Parent chain must be taken in such a way that main functional group, this is the ketone. Ketone is more important than chlorine. Chlorine is never a main functional group. It does not have any surname. So I'll start with this carbon. This carbon says I must be there. Then these two alkenes say me must be there. Then longest chain, which is going to be this cycle. So I'll start writing the name now. So it is a hex. It is a hex. Now numbering must start from ketone because that is most important functional group 1. Now whether I should go right side or I should go left side, I'll ask next person unsaturation. So alkene say I should get the lowest number. Then you get number 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It's a hex. It's a 2-ene. It's a 1-one. Hex 2-ene, 1-one. And there is a, now whatever is remaining, 4 pe methyl is remaining, starts with the M. 6 pe chloro is remaining, starts with a C. Always C will be written first because alphabetical order we follow. 6 chloro, 4 methyl. 6 chloro, 4 methyl. 6 chloro, 4 methyl, hex 2-ene, 1-one. Cyclohex. So cyclo, it's a cyclic chain. So cyclo. So it's a cyclohex 2-ene, 1-one. This is our parent chain. And then whatever is remaining in the initial we'll mention, which is 6 chloro and 4 methyl. 6 chloro, 4 methyl. Okay, this will come here. 6 chloro, 4 methyl, cyclohex. Yes, very good. Good. So this is the one. Now we'll directly go for some examples. You can see this example, everybody. So first thing is selection of parent chain. Looks like this is the longest chain that we can take here. Dodecane. Numbering should start from main functional group. I can't see any main functional group, so skip that part. Then unsaturation. No unsaturation, skip that part. Then substituent. We'll look at substituent. From this side, substituent is far away. From here, substituent is very near. So I'm numbering from here 1, 2, 3, 4, 5, 6. So 2, 4, 6, all of them are methyl. 2, 4, 6 trimethyl. Okay. dodecane, not decane, dodecane. It's a dodecane because it's a 12 carbon, and this is decane, bottom one. Okay, so these are some examples I have written here. You can take a screenshot and check them, but these are all simple examples. In your 10th class also you have done these. 10th, 11th, 12th you have kept repeating them. Okay, you can do this one and tell me what should be the answer of this. Quickly, can you tell me what should be the answer of this? Time's up. By now it should have been done. So longest chain 1, 2, 3, 4, 5, 6, 7. At down also is 7. 1, 2, 3, 4, 5, 6, 7. Both are fine. Numbering in such a way substituent comes early because there is no unsaturation. So 1, 2, 3. Here it is coming on third number. 3-ethyl, 4,4-dimethyl. 3-ethyl, 4,4-dimethyl. So D option is correct. D option is correct. One, two, three, 4, 5, 6, 7. So it's a heptane. It's a heptane. It's a heptane. 1, 2, 3, 4, 5, 6. There is just little bit of a wrong answer here, but dimethyl, 3-ethyl, 4,4-dimethyl. It's a heptane. HEP. Heptane. Okay, not. So just some typing mistake. Heptane. Just P and E is written front and back. Heptane. You can all like the video first. Okay. You can all like the video. You will be able to enjoy the video once you stay for a little long because these are simple topics going on. Now quickly we'll start with the isomerism where you will feel more difficulty, and we'll start with the electron migration effect where also you feel difficulty. Okay, these are few examples of unsaturated ones. We'll just do some problems more. You can see this one. Numbering must start from here. So this carbon must be taken 1, 2, 3, 4. So it's a but-1-ene, 3,3-dimethyl. 3,3-dimethyl but-1-ene. 3,3-dimethyl but-1-ene. Okay. Look at this one now. Again, unsaturations are here. So parent chain must be taking all the unsaturations together. 1, 2, 3, 4, 5, 6, 7. Like this. Numbering in such a way that unsaturation should get lowest number 1, 2, 3. Here it is getting 1 and 3. And the other side it is getting 1, 2, 3, 4. 1 and 4. 1 and 3 is better. 1, 2, 3, 4, 5, 6, 7. So it's a hept. See, whenever there are more than one pi bond, okay, whenever there are more than one alkene or alkyne, then don't use the word root as hept, use hepta. Use hepta. So heptatriene. Heptatriene. Now the enes are at number 136. 136. Hepta 136 trine, 136 trine, and on number 5 we have a methyl. Okay. So never say heptadiene, never say hexadiene, never say butadiene. There should be butadiene, hexadiene, pentadiene, like that. Okay. These are few more examples I have mentioned here. Quickly look at them. Quickly look at them. These are the uses of special suffix. You should remember these as well. Use of special suffix. Whenever any carbon bearing main functional group is directly attached to a ring, you have to learn this point. Whenever a carbon bearing main functional group directly attached to a ring, something like this, something like this, something like this, then we use special surname or special suffix. Special suffix or special surname will be used here. Just remember it now, the rules and all I'm not telling completely. Just learn this now. Whenever such a thing comes, then you can skip taking this carbon in the parent chain, exclude from the parent chain, exclude from the parent chain, exclude from the parent chain. There is a special rule here that whenever these functional groups are directly attached to parent chain, you exclude them from the ring. When they are directly attached to the ring, you exclude them from the ring. So our parent chain become just this: cyclopentane, benzene, cyclobutane, and then provide them special surname. So we'll call it cyclopentane. It's a aldehyde, ul, but I can't call it ul because there is a carbon also present. So we'll call it carb-ul. So carb-aldehyde. Carb-aldehyde is the special surname of this. So cyclohexane, cyclopentane carbaldehyde, benzene carbonitrile, cyclobutane carboxylic acid. So any special suffix has a carb in it, carboxylic acid. Okay, these are the ones. Okay, so practice the IUPAC nomenclature. These things will be there in your notes. You can find them. Special suffixes. Special suffixes. Okay. You can see one more example here. Let's see this example. There is no special suffix here. So, parent chain selection, main functional group is absent. Let's take alkene. This is the one. Numbering in such a way that substituent also comes early. So at number 1 we have this cyclopentyl on a ethene, cyclopentyl ethene. These are some of the examples written here. You can check them out. Let's do this one now. What should be the correct IUPAC nomenclature for this? Obviously this carbon must be number 1 because this is our main functional group. And then substituent also should come early, 1, 2, 3. So it's a 3,3-dimethyl cyclohexane 1-ol. 3,3-dimethyl cyclohexane 1-ol. Okay, just keep revising all the concepts with me. Keep brushing up your concepts. These are few of the examples. If you want, you can write them by pausing the video, but later. Okay, right now you can just continue with me. And I'll provide this same PDF in the description box by evening. Okay, by today evening you'll have all these things in the description box. You can solve all these problems yourself as well. All these you can solve yourself. This one I just told you, directly attached to the ring, cyclopropane carboxylic acid. Okay, so these are few examples written here. Anhydrides generally NEET also does not ask, so you can leave the anhydrides as well. Let's see the name of esters, because esters are also a little bit confusing ones for you. Esters. Esters I will tell you, because in esters you get confused. Esters are named as alkyl alkanoate. Okay, that is how you name esters. Alkyl alkanoate. Now what is alkyl? This is the alkyl attached after the oxygen. So a ester looks like this: R, C double bond, O, O, R dash. This is the alkyl you are writing here, alkyl. This is alkyl. And the rest of the part is called as alkanoate. So ester is a derivative of carboxylic acid. So the carboxylic acid part, R double C double bond OH, that part is called as O8, alkanoate. Other part is called as alkyl, alkyl alkanoate. So let's see two examples and move ahead. This one. So I can see here that C double bond O. So this is alkanoate. This is alkyl. This is alkyl. This is alkanoate. Quickly find the C double bond O group. Okay. C double bond O group. This is, okay, this will have a special name. This one you can see. So these are the ones with special ones. I mean, not special ones, but carboxylic acid is the main functional group here. So first one we'll mention, you can see here. So in this case, it's a 1 carbon alkanoate, means methanoate. And this alkyl will be written first isobutyl methanoate. Okay, isobutyl methanoate. For example, I can show you one more. You can see here, everybody. Let's take this one. Something like this. Okay. Now first you look for alkanoate part. COO. So this is alkanoate. This is alkanoate. And this is alkyl. 3 carbon. 1, 2, 3. This is alkyl. So alkyl is 3 carbon, which is propyl, and this is alkanoate. So name will be propyl and then name of this side. This side naming, normal rules will apply. Number 1 should be the carbon of ester, 1, 2, 3, 4. So this part is nothing but 3-chlorobutanoate. 3-chlorobutanoate. These two you can leave also, they are little bit difficult ones from the NEET point of view. Here carboxylic acid is the main functional group, so here is where the name will end. So this is oic acid, it's a oic acid. You can leave this one, this is not there for the NEET, this is not there in the NCERT as well. You can see this one. So carboxylic acid get number 1, 1, 2, 3. When ester is attached as a side substituent, then esters have a prefix called as alkoxycarbonyl. So this is a methoxycarbonyl. Again, not very important. Methoxycarbonyl on a propanoic acid. Okay, these are the ones. But we'll focus more on the important parts which are from the NEET point of view. Then they are asking which is isopropyl methanoate. Methanoate means HC double bond OO. This is methanoate. Isopropyl means a propane attached from second carbon. This is the one, which is the last option. HCOO and isopropyl. So isopropyl on a methanoate. This is about naming. Now we'll move on to the next topic, which is going to be isomerism. Isomerism. Okay, we'll quickly brush up isomerism now. Isomers are nothing but two compounds with same molecular formula but different properties. Okay. Now properties can be different because of structure. If structure is different, we call it structural isomers. If structure is same, we call it stereoisomers. If structure is same, we call it stereoisomers. Okay. So isomerism is of two types, structural and stereo. Structural isomers, how will you come to know? Whenever the name of the compound only is different. If name is different, that is going to be structural isomers. For example, if I say butane and 2-methyl propane. If I say butane, you will think of this compound. When I say 2-methyl propane, you will think of this compound. But both of them have same chemical formula, which is C4H10. So these are structural isomers. Their structure is different. But when I say D-glucose, L-glucose, both of them have same name only, no? Just the configuration is different. Both are glucose. So that is going to be not a structural isomer, but a stereoisomer. Okay? Both of them on a notebook look the same only. But when you see them in 3D, when you see them in spatial arrangement, then they look different. That is going to be stereoisomers. Now there is something called as homologues. Homologues is a very different term than isomers. Homologue means same family member with different number of carbons. Same family member, but different number of carbons. Like a family of alcohols, methanol, ethanol, butanol, they are all homologues to each other. Butanol is a homologue of decanol also. So all alcohol family people are nothing but homologues. So what are homologues? Example I am showing you, methanol, ethanol. Okay. They have same general formula. They don't have same molecular formula, but their general formula is same. For example, every alkane will be CnH2n plus 2. Okay, CnH2n plus 2. Their molecular weight will always differ by 14x units. Always differ by 14x units, or a difference of CH2 group. All of you have studied about homologues. Whereas isomers have same mass, same formula, same general formula, different properties. Okay. So these are things, few points. So I told you isomers are of two types, structural and stereo. Structural can be chain if parent chain is different, position if position of functional group or substituent is different, ring chain. One example of each I am mentioning here. Chain isomers like butane and isobutane. Position isomers like propane 1-ol and propane 2-ol. Ring chain isomers like one is in a open chain form propene, other is in a ring form cyclopropane. Both of them will have same formula, you can check. Functional isomers means different functional group. For example, aldehydes and ketones. So if I take aldehydes of 3 carbons, CH3, CH2, CHO, and ketones of 3 carbons, CH3, CO, CH3. Metamers are few special isomers where number of alkyl groups, number of carbons in the alkyl differ on the two sides of bifunctional group. So take a bifunctional group, something like secondary amine. Let me take a secondary amine. On a secondary amine, I can keep 1 carbon here, 3 here, 1 carbon here, 3 here. And if I take any other ratio like 2:2, 2 carbons here, 2 carbons here, these are metamers. These are metamers. So first one is a methyl and a propyl secondary amine. Second one is a ethyl secondary amine. These are called as metamers. All of you would have studied them before. Tautomers are ketoenol tautomers is there in your syllabus. So two isomers which exist in equilibrium with each other. Equilibrium. For example, when I take any aldehyde, CH3C double bond OH, whenever you take any aldehyde containing alpha hydrogen, that shows you tautomerism. How to do tautomerism is simple. Take the alpha hydrogen. I am taking one alpha hydrogen from here. You say sigma become pi, pi become minus, minus take the H plus. Sigma become pi, pi become minus, minus take the H plus. So it will become CH2 double bond CHOH. This is called as a enol, this is called as a keto. Keto-enol tautomerism. Keto-enol tautomerism. Just simple example I have just written here. These are the types of isomers in the structural part. They all have different names. Okay, the two structural isomers must have a different name. So by looking at the name only you can tell. Butane, isobutane, or butane and 2-methyl propane. Propane 1-ol, propane 2-ol. Propene, cyclopropane. Propanol, propanone. This name will be N-methyl propanamine, N-ethyl ethanamine. And then this is a aldehyde, ethanol. This is ethanol, ethanol. Yes, Soumya, very good question. Metamerism you choose. Soumya has a very good question here. Always choose metamerism, Soumya. So for example, if I take this ketone and this ketone, by looking they look positional isomers also. By looking at them they look like positional isomers also, but we choose metamers here. So call them as metamers. So ketone is a bifunctional group. By naming them, they look like positional isomers. They look like The names are pentane 3-one and pentane 2-one, but we'll choose metamers here, metamers being more preferred answer. Actually, both are correct. If question is, now I'll tell you what type of question. If question is, what are they? Option 1 metamer, option 2 position, option 3 functional, option 4 either 1 or 2. So answer is either 1 or 2. Okay. If the options are metamer, position, function and chain, if you don't have either both the answer, then choose metamer. So metamer is more preferred answer. Metamer is more preferred answer. Good, very good question. Next, stereoisomerism, configurational and conformational. Configurational are optical isomers and geometrical isomers. Okay, this is a very long topic. We'll cut it short down. Geometrical isomers are shown by mostly alkenes and cycloalkanes. So like butene cis and butene trans type. So cis trans is a type of GI. Both of them name is same, butene, 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 butene. IUPAC name is same. Only their spatial arrangement of groups are different. One is cis, one is trans. Optical like D and L glucose. So whenever you see configurations like D, L, R, S, okay, these are going to be okay. Good, Pawan, good. Next one. So all these things I have told you. Let's see a question. They can say, draw all the structural formulas for all the isomeric alcohols, only alcohols, having the molecular formula C4H10O. 4 carbons alcohol you have to make. So first, always you have a habit, start with the maximum carbons in the parent chain, 4 carbons. When I keep 4 carbons, then you try to think position. Okay, then you try to think position. That means if I take 4 carbons in a straight chain, how many positions I can keep OH? I can keep OH on first position or second position, because this is again first and second. So I can keep a OH here. Or I could keep the OH here. 2 options are available. Nothing else I can do. Butane 1-ol, butane 2-ol. Butane 1-ol, butane 2-ol. Now, cut down your parent chain by 1 carbon. So try to take a parent chain of 3 carbon. 1, 2, 3. So I have to keep a methyl in middle here. 2-methyl propane I have taken. Now check where can you put the OH group. The OH group can be put here, here, here. All are same only. So I'll put it here. And in this tertiary carbon also we can put, which is here like this. So answer is 4. Okay, answer is 4. 4 beta. Okay, so 4 options are there. Let me show you one more if you want. Little difficult one. All of you can quickly focus here. C5H12O, if they are asking number of alcohols. C5H12O. So you can just learn it from now on. Whenever 5 carbons are there, you can have 3 types of pentanes. 3 types of pentanes. Pentanes are of 3 types. Pentane, isopentane, neopentane. This is pentane. This is isopentane. And this is neopentane. Pentane, isopentane, neopentane. Pentane, isopentane, neopentane. Now just search for how many positions are available everywhere. In a pentane, there are 3 positions available. First position, second position, third position. So I can have pentane 1-ol, pentane 2-ol, pentane 3-ol. I can have pentane 1-ol, pentane 2-ol, pentane 3-ol. Pentane 1-ol, pentane 2-ol, pentane 3-ol. In isopentane, you have 4 positions available if you see carefully. 4 positions are available. Four positions are available. Position number 1, this is also 1, this is second, this is third, this is fourth. So I can keep a OH here, I can keep it here, I can keep it here, I can keep it here. All 4 are different names if you see. Pawan, hurry, no, 8 will come. 8 will come, you can see here. All these are different. This is a 2-methyl 1-butanol, 2-methyl 2-butanol, 3-methyl 2-butanol, 3-methyl 1-butanol. All 4 are different. And then in neopentane, you have only one position available because all carbons of neopentane are identical only. So only one option is available here. Whether I can keep a OH on this carbon, this carbon, this carbon, all are same only. So neopentyl will call this one. So 1, 2, 3, 4, 5, 6, 7, 8. 8 are possible. Okay. All 8 will have different names. First one is a pentane 1-ol, pentane 2-ol, pentane 3-ol. These 3 names I just told you. This is nothing but 1 carbon, 2 carbon, 3 carbon in the parent chain. It is 2,2-dimethyl propanol. 2,2-dimethyl propanol. If you want a proper video on the isomerism, I have kept one very, very detailed video of isomerism on this channel only. If you search for it, you will find it. Okay. If you search for it, isomerism, if you search, you will find it. I have explained how to find the isomers in very short way. And also the questions practice class that I'll take, many questions on isomerism will discuss there. Okay. Positional isomers, chain isomers, just the examples quickly let us see. Same molecular formula, same carbon length, same functional group, different position of the functional group, different position of unsaturation or a substituent. These are the examples: 1 chloro, 2 chloropropane, 1 propanol, 2 propanol, ring chain, functional isomers, alcohol and ethers, acids and esters, phenol and alcohol, very important example. Phenol and alcohol, they are different functional groups. That's why the name of second chapter in class 12th organic chemistry, the chapter name is alcohol phenol ether. Phenol is not an alcohol, phenol is a different functional group only. So remember this, these are the example of functional isomers. Primary, secondary, tertiary amines are also considered as different functional groups only. Primary, secondary, tertiary amides, cyanide and isocyanide groups are also different functional groups. One more example, let me tell you now, all of you can see here. C4H11N, how many primary, secondary, tertiary amines are possible? They are only asking primary, I'll show you all of them, how many primary, secondary, tertiary amine. So, 4 carbon can be kept as butane, I told you, or as isobutane. In butane, you will have 2 positions. In butane, you will have 2 positions. Either you can keep NH2 on number 1 or you can keep NH2 on number 2. 2 positions. Like the alcohols we made, no? In the same way. Okay. Then, isobutane also has 2 positions if you see. This position is 1, 1, 1, all are same. This is the second position. So I can keep a NH2 here or I can keep a NH2 here. So primary amines are 4 possible. Primary amines are 4 possible. Now let's look at secondary amine. Secondary amine means keeping a NH in the middle. This side also carbon will be there, this side also carbon will be there. Now total I have 4 carbons. Total I have 4 carbons. How can I dissect them? I can dissect them into 2:2 and I can dissect them into 1:3. 1:3 also. One is to 3. So this is 2:2. Now I am doing 1:3. When I do 1:3, one carbon to can only be methyl. But 3 carbon can be straight chain propyl or can be isopropyl like this. Correct? So secondary amines comes out to be 3. Secondary amines come out to be 3. Names are ethyl, N-ethyl ethanamine, N-methyl propanamine, N-methyl propane 2-amine. And then tertiary is also possible. Tertiary means keeping a nitrogen in the middle and keeping all 3 sides carbon. So I can keep 1 carbon only, there is no other way. N dimethyl methanamine. So tertiary there is 1 amine. So total amines are 8 if you see. Total amines are 8 if you see. All 8 are different. Butane 1 amine, butane 2 amine, 2 methyl propane 1 amine, 2 methyl propane 2 amine, 4 primary, 3 tertiary, 4 primary, 3 secondary, 1 tertiary. These are types of question you get in NEET. So when you get the questions in NEET, they will never exceed more than 8 or 9 isomers. Okay, at max 8 or 9, 8 only at max. They will not give you a question where isomers are coming 16, 18 and all. That is very difficult question. Okay, so you'll be able to draw up to 7, 8. Just improve your imagination like this. Is this clear? Yes or no? Soumya, Hasini, Hari, Pawan. Yes. Good. So I'll give you some for practice at home. Okay, practice them. You can practice C3H6O. C3H6O. Sir, carbon has valency 4, so it should have 4 bonds. It has 4 bonds. Everywhere carbon has 4 bonds. Whatever I have not shown are hydrogens. Okay, those hydrogens are there. Practice this, you will get, you can comment in the comment box how many you will get. 9 you should get here. 9 isomers will come for C3H6O. Little difficult one. Okay, little difficult. So you do the easier ones first. Easier ones first you do. You first do C5H12, 3 you should get. You do C6H14. After that you do C5H9Br, C5H11Br, C3H9N. These are the ones you do. Here you should get 8. Don't do it right now. Do it later. 4 carbons were there, no? Yes, there is one more carbon here. There is one more carbon here. I didn't draw this carbon. So 3 degree, only one is possible. 1:1:2. C3H9N also you will do. So you will get 1, 2, 3, 4. 4 you should get here. 4 you should get here. Okay. Now moving ahead. Metamers I just told you, so this much is sufficient. Tautomerism. Tautomerism itself is a huge topic. Just basics of tautomerism you should know. Just the basics. Don't need to go anything in depth. Who shows tautomerism, they can ask you. So you should have a C double bond O group. If a next carbon is sp3, and carries at least one hydrogen. That is the condition for tautomerism. That is the condition for tautomerism. So presence of alpha sp3 carbon carrying at least one hydrogen. Carrying at least one hydrogen. That is the condition for tautomerism. What happens here? Just remember it, how to draw the tautomer. You say sigma become pi, pi become minus, minus takes the H plus. Show a equilibrium sign and draw the next structure. C double bond C, OH, like this. This is called as a keto form. Keto does not mean ketone, keto means carbonyl, and this form called as enol form. Generally, keto form is more stable because of stable double bond. So carbon double bond oxygen is a stronger double bond than a carbon-carbon double bond. Enol form is generally unstable. So at equilibrium, keto form is always found in very high percentage, like almost more than 90%, less than 10%. Okay. Some of the enol forms are also stable, but most of the times for a simple aldehyde ketones, like for acetaldehyde, for acetone, for butanone, for them keto form is much more stable as compared to enol form. Simple. So tautomerism is a special type of functional group isomerism which arises due to transfer of hydrogen, actually proton, as a proton, from polyvalent atom to other polyvalent atom, means a carbon to oxygen, or it can come back also. Again, it will come back and go there. Such isomers are directly or readily interconvertible under ordinary conditions. They are called as tautomers. Tautomers exist in equilibrium. They keep going from one to another, one to another. The other names are desmotropism, you can leave this also, prototropism. Tautomerism is thus property shown by certain compounds exhibiting different properties as if they possess different structures, and these considered isomers are called as tautomers. So these are all simple things. You can forget about these are not in the syllabus. Keto-enol tautomerism is there for your syllabus. Okay. Keto-enol tautomerism. I have just told you, sigma become pi, pi become minus, minus takes the H plus. Conditions, I told you the conditions as well. You just worry about C double bond O group, you don't worry about any other group. So other groups also could be present, like N double bond O, C double bond N, C triple bond N, but we will only worry about C double bond O. So if a C double bond O group is present, in order for conversion from keto to enol, it must have a alpha hydrogen, just as I just told you. Okay. So these people, as you can see, they cannot show tautomerism. They cannot show tautomerism. This is your carbonyl. This is alpha carbon. Alpha carbon is sp2. Alpha carbon has to be sp3. So both of them cannot show tautomerism. Okay. Acetaldehyde can show, as I told you. Acetone can show. This is your alpha carbon is sp3. There is a hydrogen. So sigma become pi, pi become minus, minus takes the H plus. You get to the enol form. Stability part, I told you, keto is more stable than enol. Okay. Next one. Mechanism is again not there in the NCERT. So you can leave the mechanism as well. Just the basics of tautomerism only is required. That means who can show tautomerism and who cannot show tautomerism. That is sufficient. Okay, that is more than sufficient. Next one. Geometrical isomerism means cis-trans isomerism. Cis-trans and EZ. Quickly just we'll see how to check cis and trans. You can check cis and trans in cycloalkanes also, in alkenes also. Just you should know the condition of how to check cis and trans isomerism. Whenever you take a alkene will have two groups on each carbon. Two groups on each carbon. These two groups must not be same, must be different. Means M must not be equal to N and P must not be equal to R. P must not be equal to R, then isomerism will be possible. Yes, Hasini, on 23rd, 4th, I'll be keeping many questions from the GOC. Okay. You can tell me, shall we directly start with GOC or you want me to discuss the isomerism part? Shall we directly start with GOC? All of you who are watching this video, I don't know how many are there right now. Shall we go for GOC directly? Or just I will continue the way I planned. Okay. So let it be a formal video, let it be line wise only. All right. So these two groups must be different, these two groups must be different, then isomerism will be possible. So if you see here, if two groups are same, there will be no geometrical isomerism because these two groups became same. Okay. If this is X, this is Y different, if this is Y, this is X different, then it will show geometrical isomerism. Now the isomerism of cis-trans type can be another type which is called as EZ type. So let's see both the examples. All of you can see here cis-trans and EZ. Cis-trans isomerism will be there. Cis-trans isomerism will be there. One example of cis-trans, one example of EZ. Cis-trans isomerism will be there when around a carbon double bond carbon, at least one group is identical on this carbon and this carbon, at least one group, let's say hydrogen. Other group can be different, like this. So if I look at these two structures, both of them have same name. Okay, both of them have same name. Both of them are, if I start numbering from here, 1, 2, 3, it's a propene, 1 chloropropene. This is also 1 chloropropene. But the groups 2 are different here. Here also 2 groups are different. That means it will show geometrical isomerism. If same identical groups are coming at 180 degree to each other, opposite side, that is trans isomer. And if they are coming at same side, that is cis isomer. So this is cis, this is trans. This is cis, this is trans. When all 4 groups are different from each other, all 4 are different, then EZ we have to use. For example, there is a H here, there is a CH3 here, there is a COOH here, and there is a fluorine here. H here, CH3 here, fluorine here, COOH here. Now you can see these two groups are different, yes sir. These two are groups are different, yes sir. Anything identical, no sir. On this carbon and this carbon, nothing is common as well. If on both carbon, nothing is common, all are different, A, B, C, D, all different groups, then you go for EZ. How do we decide EZ? On each doubly bonded carbon, you have to rank the two groups on the basis of their atomic number. So first you will see atomic number of the directly attached atom. If atomic number is not able to decide, you will go to the next group, next attached atom. Check atomic number of next attached atom. Okay, the rules are more complex than this, but for a simple NEET level question, it will work. So check the atomic number of directly attached atom. And then check the atomic number of next attached atom. For example, here the directly attached atom is hydrogen. Here is carbon. Carbon has more atomic number. You say carbon, you are the winner. You are rank 1 for us. You are rank 1 for us. On the other side, there is a carbon and there is a fluorine. Fluorine has a more atomic number. So fluorine, you are the winner for us. Okay. So when both rank 1 come on same side, don't call it cis, call it Z. Okay. So you can remember in your brain like this, cis. Cis is Z. Okay. Cis is Z. And trans will be E. Trans will be E. Okay. Now let us look at this here. Carbon says I am the better one, so I am rank 1. Fluorine says I am the better one, so I am rank 1. 1 opposite side, so this is E. This is Z, this is E. So if all 4 groups are different, EZ will say, if at least one identical group is there, then we don't say EZ, we say cis trans. Syn NT is also there. Syn NT is valid for diazo compounds or for oximes. Again, not very important for the NEET. NEET has never asked about Syn NT. Okay, NEET has never asked about Syn NT. So just you do cis trans and EZ, which is the basic minimum one. Okay, let's see. You can see here, both hydrogen same side, cis, both hydrogen opposite side, trans. Both COOH same side or both hydrogen same side, cis. It is called as malic acid. Remember it. Cis butene dioic acid is malic acid. Trans is fumaric. Trans is fumaric. Cis trans, most common example that we give in class is malic and fumaric acid. Malic and fumaric acid, very important. Who will show GI is the question now. Quickly see. Ethene. No sir, both the groups are same. Propene. No sir, here both the groups are same. 2-methyl-butene. No sir, these 2 methyls are same. Butene, yes sir. Here hydrogen is different, methyl is different. Here hydrogen is different, methyl is different. It will show. Penta-1,3-diene. Penta-1,3-diene. This is pent 1,2,3-1,3-diene. So this will also show, you can see here, on this carbon there is a hydrogen and there is a methyl. Both are different. On this carbon also there is a hydrogen and there is a vinyl group which looks like this. So yes, this alkene, this part of the alkene will show isomerism. This part will not show because the 2 hydrogens are there. Like that you can check. Okay, so these are the ones. EZ I just told you. Some examples you can see here. Fluorine, chlorine, chlorine, bromine. Fluorine versus iodine. Iodine says I am the winner. So you are the rank 1 iodine. Chlorine, bromine, bromine is the winner. You are the rank 1 bromine. 1 same side, cis, Z. And nitrogen versus fluorine, fluorine is the winner. Nitrogen versus carbon, nitrogen is the winner. Opposite side, trans means E. Trans means E. These are the ones. If directly attached atom does not decide, then you have to go for the next atom. Like for just one example, you'll see here. Carbon, carbon, tie. Who is attached to you, carbon? He says, I am attached to carbon. I am also attached to carbon. Who else you are attached to? He says, I am attached to one more carbon. He says, I am attached to hydrogen now. So this person is the winner. This person is the winner. Carbon, carbon, tie. Who are you attached to? Hydrogen. Who are you attached to? I am attached to carbon. You are the winner. So, E. Okay. More difficult ones they don't ask generally. So, this much is sufficient. Syn NT also not required. Syn NT also not required. Now comes optical isomerism. For optical isomerism, we talk about something called as chirality. Chirality means non-superimposibility of mirror image. known superimposability of mirror image. Okay, just directly you should remember what is a chiral carbon. Chiral carbon is a sp3 carbon attached to 4 different groups. Okay, for NEET level questions, nothing more difficult, just the question can be which of the following contains a chiral carbon or which of the following can show optical isomerism. So for example, if I keep a carbon, if it is sp3 and attached to 4 different groups like hydrogen, methyl, chlorine and ethyl, then this carbon is a chiral carbon, means it cannot be cut into 2 equal halves. It cannot be cut into 2 equal halves. When something is not able to cut into 2 equal halves, its mirror image is 100% going to be non-superimposable. Its mirror image is going to be non-superimposable. Okay, how can I say that? If I show you this particular compound in a 2D projection, it may look like this. If I am a carbon, I have a hydrogen on the top, let's say, chlorine here, ethyl here, methyl here. And if I put a mirror next to it, then we know when we put a mirror around us, then only our hands will change. Left hand will become right hand, right will become left, but our head and toe remain same only. So head remains H, toe remains Cl, ethyl goes here, methyl goes here. When I try to superimpose these two, you can see that they will not superimposable. They are non-superimposable. Non-superimposable mirror images. So this will show optical isomerism. Okay. When we talk about optical isomerism, different definitions come into picture. Let's talk about them. Okay. For example, our hand is chiral. When I take my hand and put a mirror next to it, this will be the mirror image of my hand. If I try to superimpose them, they are not superimposing. Okay, they are not exactly coinciding. So our hand is chiral. Something which is not chiral is a bottle. If I take a bottle, if I take this bottle, let's say, its mirror image will exactly look same like this bottle only. And I can then coincide these two bottles together. The reason is this bottle has a symmetry. So whenever any molecule has a symmetry, its mirror image will always coincide. How it has a symmetry? I can cut this bottle into 2 equal halves like this. From the center, if I cut it, this half and this half will be identical halves. But my hand I can't cut into 2 equal halves. If I cut it like this, then this side there is a thumb, this side there is no thumb. But this bottle can be cut into half. Okay. This phone cannot be cut into half because one side there is a camera, other side there is no camera. So this phone is also chiral like that. Now, let's see some more examples. Question is, which of the following has asymmetric carbon, means chiral carbon. Asymmetric carbon means chiral carbon. So you can see here 2 hydrogens are same, 2 hydrogens are same, not chiral. 2 hydrogens are same, 2 chlorines are same, not chiral. Hydrogens are same, not chiral. Here, this carbon has a H, has a CH3, has a OH and has a different group. So this is a chiral carbon, D option. Okay, this type of questions can be asked. Which of the following has a chiral carbon or chiral carbon? Achiral means no chirality. Chiral means asymmetric carbon. Yes. Which of the following is not chiral? Little bit of a difficult question. You need to check which can be cut into 2 equal halves. If it is able to cut into 2 equal halves, cut into 2 equal halves. So, remember it now. How to check for conditions for achiral molecule. If you want any molecule to be achiral, you try to check two things. First one, plane of symmetry. And second one is center of symmetry. You can leave this question. There's a little bit of a difficult one. We'll go for the simpler ones. Center of symmetry. All of you can see here. Plane of symmetry. I'll just call it POS in simple terms, or center of symmetry. I'll call it COS. Whenever plane of symmetry is present, molecule will be achiral. Means it will not show optical isomerism. Whenever plane of symmetry is absent, molecule will be chiral. It will show optical isomerism. Same for center of symmetry. Both must be absent. Okay. None of them should be present. If anything is present, it will become achiral. If center of symmetry is present, achiral. If it is absent, chiral. Okay. So I'll draw few molecules. Center of symmetry can only be possible. Center of symmetry will only be possible in a cyclic compound. Okay. So never check center of symmetry in an open chain compound. In cyclic compound, you check. In open chain compound, sometimes it is possible, like in alkenes, trans alkene and all, but we'll not have to check it. So in cyclic compounds, you check. In cyclic molecules, you check. So all of you can see here how to check plane of symmetry, how to check center of symmetry. First example is, so first thing, always check chiral carbon. If you have a chiral carbon, then only check POS, COS. Otherwise, don't check. Okay. So, for example, this compound. This compound. This compound. And this compound. Let's take some simple examples. Now, to check plane of symmetry, so I'm checking POS, COS, POS, COS, POS, COS, POS, COS. I'm just checking present or absent. Plane of symmetry means using your hand, you try to cut the molecule into two equal halves using your hand. Now, there is no way to cut this molecule into two equal halves. If I cut it like this side is H, this side is OH. If I cut it like this, up is H, down is OH. So I can't cut it. POS is absent. COS don't check only in the open chain compound. So both are absent. POS is absent, COS is absent. So it is a chiral molecule. It will show optical isomerism. Okay, it is optically active, like that you can say. Here, I can cut it from my hand by passing my hand like this. If I cut it like this, it will cut into two equal halves. So there is a plane of symmetry present, center of symmetry not present. Any one symmetry element is present, you just call it achiral. So it is achiral, so it is optically inactive. This is chiral, so it is optically active. Next one. Yes, sir, I can cut it into equal halves. This methyl is coming out of the board. This methyl is also coming out of the board. I can cut it like this. Plane of symmetry is present. In a cyclic compound, you should also check center of symmetry. Center of symmetry means start from the middle of the compound, go in any one direction, and then go diagonally opposite direction. You should get same atom. You should get same atom. Now, this methyl is actually not on this board. It is out of this board. So, it is like this. All of you can see here. It is like this. This methyl is out of the board. This methyl is also out of the board. So, this structure looks like this. Plane of symmetry, so I just concluded that plane of symmetry is there. But center of symmetry, let us see. If I start from center, if I go out of the plane, I get methyl. I should go behind the plane, I don't get a methyl, I get a hydrogen. So there is no center of symmetry. There is no center of symmetry. Whereas in this one, you can see a center of symmetry. This one looks like this. One methyl is out of the board, one methyl is other side of the board. Okay, now you can see, yes sir, there is a center of symmetry. I can go up, get a methyl, go down, get a methyl. Yes, center of symmetry is present. Here plane of symmetry is also present. I can cut it with my hand like this. I can cut it with my hand vertically like this. So there is a plane of symmetry also present. So these both are achiral. This is also optically inactive. This is also optically inactive. Any one symmetry element makes it optically inactive. Okay. These are the basic things which can be asked for your NEET. Okay, because within 3 hours you have to do a lot of topics. So just the basic touch up we are doing so that all the concepts get clear. And on 23rd or 24th, as I told you, on 23rd or 24th April, there is one question practice class. Questions will practice there only. Okay, just touching up the concepts here. In the questions, I'll tell you that how to convert a Fisher to a wedge dash formula to a Fisher formula if you don't know. Questions I'll tell that time only. Now, once you have a Fisher projection like this, then you can talk about its configuration. Just like there was cis trans and EZ in the case of geometrical isomers, there is a configuration called as RS in the case of optical isomerism. RS. So we can see here configuration in optical isomerism. One example of each. We either use RS configuration or we use DL configuration. Big D, big L. There is small d, small l also. It is completely experimental. So this one has to be calculated using a polarimetry experiment. RS is easy to check. If any chiral carbon is given like this, let's say OH is here, a CH3 is here, a hydrogen is here, and a NH3 is here, or another one is given like this. Let's say a COOH is here, let's say a hydrogen is here, let's say a methyl is here, and a chlorine is here. So this is a chiral carbon, as all of you can see. It is attached to 4 different groups. This is also chiral carbon. On a chiral carbon, how to tell RS configuration? The 4 groups which are there, using the same EZ nomenclature rules, atomic number and the atomic number of next attached atom, you try to rank all 4 of them. So here, oxygen versus carbon versus hydrogen versus nitrogen. Oxygen is the best, you get rank 1. then nitrogen, second best atomic number, rank 2, rank 3, rank 4. No, Pawan beta, no. Then turn your pen from 1 to 2 to 3. Go from 1 to 2 to 3. Go from 1 to 2 to 3. When you go from 1 to 2 to 3, check where is the fourth group. If fourth group is vertical, means on this line, then clockwise is R, anti-clockwise is S. If fourth group is horizontal, then opposite, clockwise is S, anti-clockwise is R. Okay, this is the rules. So you can just see here, I am going from 1 to 2 to 3, fourth is vertical, so this rule has to be followed. 1 to 2, 2 to 3. I am moving anti-clockwise. Anti-clockwise. So it is S configuration. It's a S configuration. Whereas the next one, let's do their numbering. So chlorine, rank 1, very high atomic number. Carbon, carbon, same. Carbon after this oxygen is there. So this is rank 2. This is rank 3. This is rank 4. Fourth is horizontal. So I'll use this particular way. Going from 1 to 2, 2 to 3. 1 to 2, 2 to 3. Clockwise. Clockwise, fourth is horizontal. Clockwise is S. So this is also S configuration. Like that you can say RS configuration. Okay. Next I'll show you DL configuration. Big D, big L, not small d, small l. Whenever you have a sugar, monosaccharide sugar like glucose, this is how glucose looks like. Whenever you take a sugar, there are going to be so many, hydroxyl groups, CHOH, 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 CHOH. Go to the last chiral carbon. You can see that this is also chiral carbon, this is also chiral carbon, this is also chiral, this is also chiral. Go to the last chiral carbon, which is here. If OH is present on right hand side, it is D glucose. Only the last chiral carbons OH you will see, keeping the most oxidized aldehyde on the top. Where is the last chiral carbon? Here. If its OH is on the right hand side, it is D, and its mirror image is L. Its mirror image is L. So make a mirror. Shift everything this side. OH, OH, H, OH. Mirror image. This is L, L glucose. This is L glucose. Okay, this is DL. Small d, small l, we cannot decide. That is completely decided by the polarimetry experiment. Experiment not that much important. You can see from the NCERT. Now, this is about optical isomerism. Next, we have electronic effects. Electronic effects. This is the last part of GOC chapter of 11th class GOC chapter. Electronic effects are of two types: permanent and temporary. You can remember the names. Permanent effects are also called as polarization effect. Polarization. And temporary is called as polarizability. These are three. Permanent are three: inductive, mesomeric, and hyperconjugation. IMH. Inductive, mesomeric, hyperconjugation. Inductive is of two types: minus I plus I. Mesomeric is of two types: minus M plus M. Hyperconjugation is of two types, minus H plus H. Temporary only one is there, electromeric effect. Again it is of two types, minus E plus C. We'll remember the groups who show these effects. Minus I means electron withdrawing groups. The best one is NO2, then OH, CHO. These are all minus M groups. Any group which contains more electronegative atom than carbon. Fluorine, chlorine, bromine, iodine, CHO, oxygen is there, SO3H, oxygens are there. Fluorine, chlorine, bromine, iodine, these are all minus I. Who is the plus I group? A plus I group is generally an alkyl group. CH3, ethyl, propyl, isopropyl, these are all plus I. Okay, so minus I plus I just told you. What are the applications of minus I and plus I? There are many major applications. Okay, there are many major applications like the electronic effects can help you to decide the acidic character, basic character, stability of carbocation, stability of carbon ion. Okay, all of us will see the first one here. First one, if I want to check stability of carbocation and carbon ion. Carbocation and carbon ion. So when I look at different types of carbocations, like this one, this one, and this one. And if I look at same types of carbon ions, like this. Then beta, carbon ion is already very rich of electrons. Okay, carbon ion is already very rich of electrons. And if someone already has a lot of electrons, you don't supply them electrons. If you supply them electrons, in that case, it will become more unstable. Nobody wants to remain charged. Everyone wants to lose their charge. So here a positive charge, methyl group we know is a plus I group. So it is sending electrons, plus I, 2 plus I's. And here 3 plus I's. 3 plus I's. So this carbocation will be very happy that I was positive and I got a lot of electrons, so I am becoming neutral. This is not good. So primary, secondary, tertiary carbocation, always tertiary carbocation is better. And in the carbon ion, it is opposite. In the carbon ion, it is opposite. Already a negative person and you are sending minus I, plus I, you are sending more and more electrons to it. It will become very, very unstable. It will become very, very unstable. So when you don't give him electrons, he is more happy because you are already negative charge. Okay, that is how we can check plus I minus I, simple application. Okay. Then, before studying mesomeric effect, we should know what is resonance. Okay, all of us have an idea what is resonance. Okay, I'll just open the resonance part. Just a second. Okay. Just a little bit of basics we'll see. Whenever you want to see resonance, first thing you should know what is the meaning of conjugation. A conjugation means at alternate position, there should be either pi bonds present, lone pair present, or positive charge or negative charge present. It is becoming little slow. I'll just open a new file and do. Okay. So just to know about resonance, we should know about conjugation. Conjugation means presence of alternate pi bonds, plus charge, negative charge, or free radical, or lone pair. Whenever these things are present, there will be mesomeric effect. Whenever there is a conjugation, there will be mesomeric effect. For example, let me take this example. I am keeping a benzene here and putting a NH2 group here. I am putting a benzene here and putting another group here, which is aldehydic group. Okay, so there are few functional groups which supply electron to the benzene ring. These are called as electron donating functional groups, which are the functional groups which looks like this. Any group which carry a lone pair. It may be NH2, it may be OH, it may be Cl, okay, it may be OR, ether. These all groups are called as plus M groups. Plus M, electron donating groups. Electron donating groups. So what they do is they send the resonance like this. Lone pair become pi, pi become minus. Okay, lone pair become pi, pi become minus. So the next structure starts looking like this. Then minus become pi, pi become minus. Next structure starts looking like this. Minus become pi, pi become minus. Next structure starts looking like this, and so on. These are called as resonating structures. Minus become pi, pi become minus. So we come back to the original looking structure like this. These are the resonating structures of aniline. Okay, these are the resonating structures of aniline. Now what is happening here is whenever electron donating group is present, you can see it sends electron only to its ortho position, its para position, and its ortho position. Okay, so the plus M groups, the electron donating groups are considered to be two things. One is they are electron donating group, so they are ring activating group. Any group which increase the electron density in the ring are called as ring activating group because they increase the electron density. And also they are called as ortho-para directing group. They have ortho-para directing nature. Means whenever any electrophilic substitution will happen, Harshita is saying trick for minus I. Yes, Harshita, there is a trick for minus I. Okay, there is a trick for minus I. They are also called as ortho-para directing in nature. Why they are called as ortho-para directing in nature is because whenever there is a plus M group attached and I do a electrophilic substitution reaction on that benzene ring, electrophilic substitution reaction, reaction. That means the electrophile is coming to attack. Electrophile is having a positive charge. Then this NH2 group will say, I will decide where you will go and attach. NH2 says, I have sent electrons on the ortho position and para position. So my ortho position is electron rich and my para position is electron rich. So if you want to go and attach somewhere, please go and attach there. So that's why electrophile will attack on ortho position and para position. That's why they are called as ortho-para directing groups. Okay. So what do plus M groups do? So NH2 has two effects. I just told you it has a minus I also and plus M also. Inductive effect never decides the direction where electrophile will go. It is all decided by the mesomeric effect. Okay. So this is the one. Two things about plus M I just told you. Two things about minus M. When we talk about minus M effect, it is shown by groups which are of type A double bond B type. Means any double bond or triple bond is present. Harshita, minus I trick you want, I'll just write it here, minus I order. You can remember it as okay, this is the order of minus I, Harshita. So here you can learn it in little bit of Hindi. Okay. So what is the trick? Trick is simple. There are two police cases which are going on. Okay. One police case is about a hit and run case. Other police case is to find who is the mother of alcohol, whether the mother of alcohol is alkyne or benzene. Okay, so two police cases were there. These two police cases were handled by a father and a brother. Father is a collector, brother is an inspector. Okay, like this we'll learn it. And it's a high profile hit and run case. So they were searching for, celebrities like Farhan Akhtar, Hrithik Roshan, Shah Rukh Khan, Naughty Salman and all. But they finally found that the hit and run, the car belongs to some other person whose name is Sonu Chaudhary. So I'll just tell you what is this. You can just remember it now. Na Farhan, na Hrithik Shah Rukh. Na Farhan, na Hrithik Shah Rukh. Na hi Naughty Salman. Salman means sulfonic acid. Na Farhan, na Hrithik Shah Rukh. Na hi Naughty Salman. Sonu Chaudhary ki car mein. Sonu Chaudhary car mein means none of them was there in the Sonu Chaudhary's car. It was Sonu Chaudhary's car who did the hit and run accident. Na Farhan, na Hrithik Shah Rukh, na hi Naughty Salman, Sonu Chaudhary ki car mein. Okay, so first case is solved. First case is solved. Father collector, brother inspector. Father collector, brother inspector. And then came the second case. We came to know alcohol's mother is not alkyne, but it is benzene. Alcohol's mother alkyne nahi, benzene hai. Benzene hai. Alcohol's mother alkyne nahi, benzene hai. Like that you can say. Alcohol's mother is not alkyne, but benzene. Okay. Only minus I priority is one to be learnt. Okay. Plus I priority is simple. A more bulkier a more bulkier alkyl, like tertiary butyl has more plus I, then isopropyl, then a ethyl, then a methyl, then tritium, and then deuterium. This is the plus side. Minus M plus M is not required to learn only. Okay. From minus M plus M, I'll tell you what you can learn just after we do minus M. So minus M groups are like CHO, A double bond B type, like aldehydic group, like ketonic group, like amide, like carboxylic acid, and so on, like NO2, one of the most deactivating. They pull the electrons away from the benzene ring, but they pull the electron only from ortho and para position only. So whenever you do any resonance, please remember that plus M people send electron to ortho and para position, minus M people just pull from ortho and para position like this. Minus become pi, pi become minus. So next structure starts looking like this. You get a positive charge on the ortho position. Then pi moves ahead. Positive charge comes to para position. Then next pi moves ahead. Positive charge comes back to ortho position. And then we get back to the main structure as well. Minus become pi, pi moves ahead. Like this. So this is the one. So you can see here what is happening in the structures is, whenever any minus M group is attached here, it is just pulling electrons from ortho and para position. Pulling from here, pulling from here, pulling from here. Making positive charge at ortho and para position. So because they are electron sucking in nature, they are ring deactivating groups. So minus M groups are ring deactivating in nature. And they are meta-directing in nature. They are meta-directing in nature. Okay. Ring activating, ring deactivating, and meta-directing. Why meta-directing? Because whenever an electrophile will come to them, in that case, electrophile will say, please give me electrons. These groups will say that I have pulled all the electrons from my ortho and para position. So if you want to attach, you go to meta position. So they become meta-directing groups. So one important order to learn here from here is reactivity order for electrophilic substitution reaction. Okay, most reactive people are those who have a plus M group. Then comes benzene, and then comes minus M group. Then comes minus M group. So for example, a phenol is very reactive for electrophilic substitution as compared to a benzene. Here one exception comes, halobenzene, means chlorobenzene. Although it is a plus M group, but the plus M of chlorine is negligible. Plus M is negligible. So instead of plus M, we consider minus I effect. Minus I is much stronger than plus M. So chlorine is behaving like a minus I group only. Chlorine behaves like a minus I group only. And then comes the minus M groups like NO2. So this is the order. You can learn this order. This type of questions can be asked in the NEET. Okay. You can write it down. Okay, we'll take a break of 5 minutes. I'll just open the timer here. We'll take a break of 5 minutes so that you can also drink some water, have some snacks, and then we'll start again. Okay, everyone. This class will keep for only general organic chemistry part, okay, not the whole organic, because anyways it's not possible to complete in 3 hours. Whatever time we have, I'll be explaining you the GOC completely, okay. Next one, applications of mesomeric effect. Applications of mesomeric effect. One of the important application of mesomeric effect, let's do the first one, which is to find acidic character of phenols and benzoic acid. So you should remember that whenever you take any phenol, phenol is an acidic compound because after leaving H plus, if when phenol acts like an acid, this is how phenol will dissociate. It will leave the proton and make this ion called as phenoxide ion in water when you are doing this. So phenol breaks down like this to give phenoxide and hydronium. Now, if I stabilize this phenoxide ion more and more, reaction will go more and more forward and phenol will become good acid. So we can say acidic strength of phenol or even carboxylic acid or benzoic acid is directly proportional to stability of conjugate base. Okay, this is known as conjugate base. So whenever an acid loses a proton, the product that is formed is called as a conjugate base. If conjugate base is stable, in that case, the acid will be more and more stronger acid. Now, can you see a conjugate base itself is like a carbon ion, it's a negatively charged species. So to stabilize this negatively charged species, I should apply a minus M or minus I group. So minus M or minus I group will make him very happy. A plus M or plus I group will make it very sad. So I can say stability of conjugate base directly proportional to electron withdrawing group. Which is minus M and minus I, inversely to electron donating group, which is plus M and plus I. The most common example I'll just show you here. For example, when they say write the acidic strength order for the following phenols. I have a phenol, I have a para-nitrophenol, I have a para-methoxyphenol, and I have a para-tertiary butyl phenol like this. Okay, when a question comes like this, Harshita, there will be one question practice class, as you know, in that all hydrocarbons and haloalkane, haloarenes, everything will be discussed there. Okay, I hope you understand that within 3 hours, full 11th and 12th is impossible to complete. So this is mostly 11th class we'll do here, and the reaction part will be done then in the 23rd. Physical chemistry already Amit sir has taken a class, I think day before yesterday. You can see that in the live option there will be that class also present. Okay, you can see that as well. Now look at the groups now. These are all phenols. Here NO2 is attached, which is a minus M. It is pulling electrons from ortho and para position. So it is pulling from here, it is pulling from here, it is pulling from here. Means it is pulling from your O. It will be very, very happy. OCH3 is a plus M group. Plus M group. It is sending electron. Plus M group sends electron to ortho and para. It is sending to the OH. It will be a very bad acid. Okay. It will be a very bad acid. This is a plus I group. Plus I group, actually inductive effect is distance dependent. Since the distance is very far away, it is almost like normal only. There is no much effect. Okay, neither happy nor sad. And this one is also neither happy nor sad. At least some plus I is there, so it will be kind of unhappy because some electrons are reaching there. Here nobody is sending, nobody is pulling, so he is a neutral person, not very good, not very bad. So the best acid becomes option B. Best acid become option B. Worst acid become option C because someone is sending electron. C is bad because of plus M. Inductive effect is always a weaker effect as compared to the mesomeric effect. So meso is always a strong effect. So strong sending, very bad. Weakly sending, so it is also not very good. So D and A comes here. Okay. So B is pulling. Someone is pulling electron, that is very good. Then A, neither pulling nor giving. Next one is OCH3, which is plus M, very, very bad. And D has plus I, that is also kind of. So anything with a plus effect, plus I, not good. Plus M, not at all good, because plus M is very strong effect. Minus M is very, very good. And no effect is somewhere in the middle, like this. Same would go for the carboxylic acid also. If there was a COH on the top, then also same order. So that's the first application. Second application is basic strength of amines, just the opposite case. When you say basic strength, opposite you have to check. Basic nature of amines. Basic nature of amines. Especially aniline I am talking about here. So when I take a aniline, which looks like this, and it goes into water, it acts like a Bronsted base, means it collects a H+. So it becomes anilinium ion, NH3 positive, like this. This is how it acts like a base. Dissociation constant is called as Kb for a base. Correct? Yes. So we can say, if I want to stabilize this conjugate acid, so this person is a base, then this person becomes a conjugate acid. It is like a carbocation only, it has a positive charge. So to stabilize a conjugate acid, a electron donating group plus M plus I will stabilize this, whereas minus M or minus I will destabilize this. Minus M or minus I will destabilize it. So donors make base good, donors increase the basicity, withdrawers increase the acidity. You should remember this. Okay, as a note we can remember it. Donors increase the basic strength. Okay, donor means plus M people and plus I people. Whereas pullers, electron pulling group, means minus M and minus I, increases the acidic strength. Increases the acidic strength. Okay. So let us see one example here. Like if I write the basic strength order. This is aniline. Aniline with a NO2 aniline with a Cl, aniline with a OCH3, or aniline without anything. If these are the groups present, I'll just call them as A, B, C, D. I'll just check what are the other functional groups doing to NH2. NO2 is a minus M group. Minus M group. It is pulling electron. Pullers make the base bad. So this is very bad base. It will be crying. Very bad base. Cl is plus M, but plus M is negligible. So we consider only minus I. Minus I also will pull some electron, but because it is far away, minus I is very negligible. This is also not good. OCH3 is a plus M group. Plus M group. It is sending electrons to ortho and para. So it is sending electron to your NH2, making it very, very good base. Plus M makes it a very, very good base. And the last one is without anything, so it will be moderate. So who becomes the best? The best is best is C, then D, then B unhappy, A is crying only. So electron donating group makes the base stronger. Electron withdrawing group makes the base weaker, like this. Okay, so these are the things where mesomeric effect is used. Next we'll do hyperconjugation effect. The third effect, permanent effect, hyperconjugation. It is also known as no bond resonance. Okay, no bond resonance. Condition is like tautomerism type of condition. Condition is you should have presence of alpha hydrogens on sp3 carbon directly attached to three of the groups. So in the sir, what if amine is attached to unsaturated hydrocarbon? Will lone pair density affect stability? Yes, Harshita. If your doubt is this, if this is your doubt, this versus this, I hope that this is your doubt, what you are asking. This amine versus this amine. In this case, you can see that lone pair are moving in this direction due to resonance. So this vinyl group is acting like a minus M for him. It is pulling electron from NH2. Whereas here the electrons are not going for delocalization. So this is acting like a plus I for it. So this is good base. This is bad base. I hope this was your doubt. Yes. Okay. Good. Next. Condition for hyperconjugation is alpha hydrogen on a sp3 carbon directly attached to either a alkene or a carbocation or a carbon free radical. So in these three cases hyperconjugations occur. More the alpha hydrogen, more the stability. More alpha hydrogen, more the stability. Whether you are checking stability of alkene or you are checking stability of carbocation or you are checking stability of free radical. Okay, so alpha hydrogens decide the stability of alkene, carbocation and free radical. Before checking inductive effect, always you check alpha hydrogens. If alpha hydrogens are more, stability is more. Let us see. Like for example, just find how many alpha hydrogens are there. CH3, CH double bond CH2, CH3, C double bond C, CH3, 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 CH2 double bond CH2. If they say stability order, you tell stability. then what you need to do is, as soon as you see a alkene, put a star there, that next to the star will be alpha. So this is alpha carbon. Here there are 3 alpha hydrogens. Alpha, 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 alpha. So there are 3, 3, 3, 3, 12 alpha hydrogens. Here no alpha, 0 alpha hydrogens. So more the alpha hydrogens, more the stability. This is most stable. This is least stable, and this is in middle. Okay. Same thing will work for a carbocation as well. This carbocation versus this carbocation versus this carbocation versus this carbocation. So if I have these 4 carbocations and they ask for the stability, here also I ask stability, here also I am asking stability. So to check stability here, next to carbocation, so wherever you see carbocation, put a star there, put a star there, put a star there, put a star there. Just next to carbocation is alpha carbon. So here, this is alpha, this is alpha, this is alpha. 3 alpha hydrogens are here, 2 alpha hydrogens are here, 2 are here. 3 plus 2 plus 2, total there are 7 alpha hydrogens. Here only 1 alpha carbon, which has 1 hydrogen. So 1 alpha hydrogen. Here this is alpha, 2 alpha hydrogens here, 1 alpha hydrogen here, only 3 alpha hydrogens. This has 2 alpha here, 2 alpha here, 4 alpha hydrogens. So more the alpha hydrogens, more the stability. This is the best. This is very, very bad. This is moderate. This is also stable. Okay. So 1, 4, 3, 2. This will be the order. Same for free radical also works. If I give you free radical, in the same way you will check. If I give you CH3 radical, CH3 CH2 radical, CH3 CH radical CH3, CH3 C radical CH3 CH3. Okay, if I give you these. Same way you will check. Wherever you see a radical, just put a star there, put a star there, put a star here, put a star here, put a star here. Next is alpha. Next carbon is alpha. There is no next carbon here. 0 alpha hydrogen. Here 3 alpha hydrogens. Here 3 plus 3, 6 alpha hydrogens. Here 9 alpha hydrogens. So the best one is 4th one. This is most stable. And this is least stable. That's why we say tertiary carbocations are more stable than primary carbocations. Tertiary radicals are more stable than. So whenever you check hyperconjugation, only check it in alkenes, carbocations and radicals. Never check it in carbanions. Carbanions don't have any hyperconjugation. Carbanions do not have any hyperconjugation. So for carbanions, you check only inductive effect. Okay. Harshita, if you have a doubt, please ask any doubt. Okay. Because I see that you are doing it and you are doing well. If any doubt you have, any particular topic you have, next half an hour, I'll explain that. Next half an hour, I'll explain that. Whichever topic you feel like you want to know, just mention that. Half an hour, I'll explain that. These are the effects. A particular topic you want to know, Harshita? And Hasini, any particular topic? 15 minutes, both of you, one topic I'll explain. GOC is completed over here. Yes, you can tell me. Okay, I'll wait for the message, then I'll start. Elimination reaction. Okay, Harshita. So let me tell you about elimination mechanisms. Beta, there are three types of elimination reactions which are there for your syllabus. Three types. One is E2 mechanism. We call it bimolecular elimination. Just whatever I am telling you, that is more than sufficient. E1 mechanism, which is called as unimolecular. One is called as E1 CB mechanism, which is not very important. First two are very, very important. Remember where the E2 happens. Rearrangement possibilities I'll tell you. E2 happens in alkyl halides. E1 happens in alcohols mostly. E1 CB happens in alkyl fluoride mostly. Okay. So I'll start with E1 so that you know the rearrangement possibilities. See here, when to do rearrangement? E1 mechanism. Whenever you do acid catalyzed dehydration of alcohols, acid catalyzed dehydration of alcohols, this is a headache reaction. Headache reaction because rearrangement is possible. You see here quickly. Whenever you see any alcohol given to you, let's say this alcohol is given to you. Let me take one more carbon here. Okay, let's say this alcohol is given to you, or let's say this alcohol is given to you. Keep a hydrogen here, or just keep a CH3 here, or this alcohol is given to you. And they say concentrated H2SO4, 170 degrees Celsius heat. Or something like this is given to you. Okay. Now, the very first thing what happens when alcohol is heated with the acid is alcohol collects a H plus from the sulfuric acid and become H2O positive. So this will just collect a H plus. This will just collect a H plus. This will just collect a H plus. This is E1 mechanism. So what happens here is from here H2O will go out. From here H2O will go out. From here H2O will go out. So in the very first step you make a carbocation. CH3, C, CH3, CH3, CH positive, CH3, like this. Same way I'll make the carbocation here. Same way I'll make the carbocation here. Like this. Now remember, whenever you get a carbocation, carbocation asks to the next carbon, neighbor carbon. It will ask, do you want my plus? Do you want my positive charge? Neighbor will say, yes, I want your positive charge. If neighbor can become a better carbocation. If neighbor can stabilize the positive charge more, it will say, yes, I need your plus. If neighbor cannot stabilize the carbocation, then it will say, no, I don't need your plus. So we'll ask to neighbor. If neighbor says, yes, I need your plus, then what you will do is, you will say to neighbor, okay, transfer your hydride to me, H minus. If you don't have a hydride, you transfer your methyl group to me. So you send me 2 electrons. How will you become positive? You will only become positive after losing 2 electrons. So you send me 2 electrons with a hydrogen or send me 2 electrons with a methyl, like that. See here. So this carbon is asking to the neighbor, do you want my plus? Do you want plus? This carbon to will say, no, I am primary, you are secondary. Okay, I mean this person is asking, this person is asking to the neighbor. It says, no, I don't need your plus, I am primary, you are secondary, you are already better than me. But this carbon will say, yes, I need your plus. Because I look like a more substituted carbon, you are just a secondary carbon. I can stabilize the carbocation more because I am a tertiary. So this person says, okay, you want my plus, then you send me your hydrogen. This carbon says, I don't have a hydrogen, so I'll send you methyl. So take these 2 electrons of methyl along with methyl and send it here like this. Send it here like this. So what happens here? There is a methyl shift happening. CH3 minus shift. Shift always occur between 2 neighbors, never from the alternate position, always from the adjacent position, next position only. So what does it become? It becomes CH3, C, CH3, CH, CH3. This methyl has just shifted here. So this carbon become electron deficient now. This carbon become electron deficient now. Okay. Now it will keep asking, you keep asking, again ask, do you want my plus? He says no, he says no, he says no. Obviously from a tertiary, carbocation never wants to go to primary. From a tertiary to tertiary will be same only, so no need. So this is the final carbocation. Now do the beta deprotonation, which is the last step, to make ZZ product. So now for this carbon, this is a beta carbon, this is a beta carbon, this is a beta carbon. We know that more substituted alkene is better. So now the H will go out from here, H plus will go out from here, and you get this as the product. 2,3 dimethyl butene. 2,2 dimethyl butene. Okay, same way I am telling the next one, you can see here. Carbocation asks the neighbor, do you want my plus? This neighbor say, yes, I want your plus. I am sending you methyl. Methyl comes here. So carbocation is formed here. Then go for the ZZ product, which is more substituted alkene. Is it clear, Harshita? Is this clear, Harshita? Sir, biomolecule structures, please. Samir, which particular structures you are asking? Are you asking alpha beta glucose? Are you asking about amino acids? Which part? You can see the next one now. Whenever you see such a scenario that outside a 4 or 5 membered ring, there is a positive charge. outside a 4 or 5 membered ring there is a positive charge, then don't do any hydride shift, don't do any methyl shift, do ring expansion. Remember it now. So this one asks to the neighbor, do you want my plus? Neighbor says, yes, I want your plus. Yes, I want your plus. So if you do hydride shift, there will be a problem. Let's say this hydrogen, you try to send it here and you make it look like this. Okay, although it looks like a tertiary carbocation, but it is a very unstable carbocation because here bond angle is only 90 degree and carbocation always try to achieve 120 degree angle. So it says I am not happy here because of angle strain. So don't send me your hydride, do something else. Do something else. So hydride shift you will not do. Now what is that something else? It says give me some other electrons. Give me some other electrons. So this neighbor says, okay, if you are not happy with the hydrogen, then I'll have to give you these 2 electrons because I don't have any other bond. Either you take this bond or you take this bond. So you will do here bond shifting. This bond will pluck from here and give to this carbon. So what has happened here, you see? This was the initial case. Okay, it was like this. Now what has happened is this bond, we plugged it from here like this and we gave it to that carbon. We gave it to that carbon like this. Okay, we pluck it from here, gave it to that carbon. So the carbon where we plugged the bond from, that becomes positive. That becomes positive. That becomes positive. Now the ring has become 5 membered ring. 1, 2, 3, 4, 5. So I can draw it like this. 5 membered ring with a plus charge and a methyl on the next position. We call it ring expansion. Don't stop here. Ask your neighbor again. Do you want my plus? Neighbor will say yes. You are secondary. I can become tertiary. Then send your hydride. Okay, sending my hydride. Sends here. And the carbocation become tertiary. This is a very stable carbocation. Now it is happy. Now go for elimination of proton and get your final product as alkene. So 4 membered ring always go to a 5 membered ring. If there was a plus charge outside the 5 membered ring, that would become a 6 membered ring. You can try this one yourself now, Harshita. Can you try this one now and tell me what you will get as the product? Can you tell me the IUPAC name of the product here? Okay. Hexene, cyclohexene, very good, very good. So from here you have removed the water after taking a H plus. So you get a carbocation which looks like this. Then you are doing a ring expansion which looks like this, which is cyclohexyl carbocation. Then doing the elimination and finally reaching to cyclohexene. That's good. Yes, good, good, good. All right. Okay, so Samir is asking, sir, polysaccharides and disaccharides. Okay, Samir, you see here, sir, Samir. First, I'll make you remember the structure of glucose. Glucose has this is the open chain structure of glucose. OH, OH, H, OH, like this you can remember. OH, OH, H, OH. Then there are two cyclic structures of glucose also, which are formed by hemiketal formation, which looks like this. This oxygen attacks on this aldehyde as nucleophilic addition, the fifth carbon's oxygen, this oxygen. From here it attacks like this, O becomes OH. So the next structures look like this. So the OH there can open on the left hand side or right hand side. So two possibilities are there. This from here the oxygen has attacked like this. Rest everything is same. OH, OH, H, OH. So glucose, fifth carbon's oxygen, the OH group, attacks on the carbonyl group and makes a cyclic structure, which is a hemiacetal structure, which looks like this. If OH is on the right hand side, we call it alpha glucose. If the OH on the first carbon, this is the first carbon, that is called as anomeric OH. Anomeric OH. If it is on right hand side, we call it alpha glucose. If it opened on the left hand side, we call it beta glucose. So beta glucose also will look like this, just the position of OH will be opposite side. Here H, here OH. This is beta. We call it glucopyranose because pyran is a 6-membered ring and glucose also has a 6-membered ring. So this is alpha glucopyranose. This is beta glucopyranose. Now you should know how to convert these structures into something called as a Haworth projection. In a Haworth projection, you will draw it like this, like a 6-membered ring. These two carbons are actually coming out of your notebook. So I am just drawing it little more bold as a thick line. They are actually coming out of your board, something like this. Now, each carbon has two groups now. This is carbon number 1. Remember it. This is carbon number 1, carbon number 2, carbon number 3, 4, 5. Okay. There are two groups on each carbon. One you draw up, one you draw down. Up, down, up, down, up, down, up, down, up, down. Same thing here. Remember it. Whatever is right is down. Whatever is left is up. Right goes down. Left goes up. So, carbon number 1, OH right means OH down. Carbon number 2, OH right means OH down. Carbon number 3, OH left means OH up. Carbon number 4, OH right means OH down. Carbon number 5, anyways there is no right and left, always show CH2OH up. So H down. This is the structure of alpha glucose. And beta glucose is easy to remember. Just remember ud, up, down, up, down. Up OH, down OH. Up OH, down OH. Ud. CH2OH. So what I have done here, you can see here is alpha I told you how to draw. Then I just changed the position of first carbon. First carbon ka OH was down, I put it up. Rest everything is same. So this is down, down, up, down. This is up, down, up, down. This is ud, up, down, up, down. This is down, down, up, down. Down, down, up, down. Sir, electrophilic addition and electrophilic substitution. And when alpha and beta elimination takes place for reagents. Harshita, you will have to wait for the next class for this. Okay, I'll on the next class, that is questions class, there I'll bring all these questions. I'll keep it in mind. Okay, 22nd, 23rd, just see when the class will be put up. I don't know the exact date. That day I'll explain. So this is alpha glucose, DDUD, down, down, up, down. Position of OH I'm telling. Position of OH, down, down, up, down. Here up, down, up, down. Once you have remembered glucose, you can remember galactose. Galactose is same as glucose. Galactose is same as glucose, just fourth carbon is reverse. Fourth carbon. Only fourth carbon. This is glucose. This is going to be galactose. Fourth carbon. See here. 1, 2, 3, 4. Fourth carbon OH. I am keeping it up. H down. This is, so this was beta glucose, beta glucopyranose. This was beta glucopyranose. This is beta galactopyranose. Beta galactopyranose. This is alpha galactopyranose if I change the fourth carbon's position. Fourth carbon pe if I change the configuration, that will become alpha galactopyranose. Just fourth carbon I am changing. On the fourth carbon, OH was down, now I am taking it up. This is beta galactopyranose. Is it clear? Sir, the final product of reaction of ethyl bromide with H2S in the presence of KOH. H2S in the presence of KOH. It will just produce a potassium sulfide. So the reaction is going to give you a thioether. Okay. H2S in the presence of KOH that you are saying, this is nothing but potassium sulfide plus H2. Okay. If you have seen this reagent anywhere, then you are asking this doubt, because in the reaction ethyl bromide you are reacting it with. So ethyl bromide, when it reacts with K2S, so it will be like something like a Woods reaction, where one bromine will go from here, one more bromine will go from there, and you will get a thioether. You will get a thioether if you reacted with K2S, one equivalent. So 2 KBr go out like this, one sulfur will attach to the middle, giving you this. Okay, so that is all about it. We'll keep the class till here. I hope you guys have enjoyed. Okay, the time is almost up. I'll meet you again after a few days with the 100 more important questions on organic and inorganic as well as physical chemistry. We'll see what to do. Okay, chalo, take care, bye bye, thank you very much. Please like the video before you go out of the class, and I'll see you all very soon. Bye bye.